Hello, in this video we are demonstrating the 5G ready 40 MHz to 12.4 GHz RF and microwave antenna training lab MAT12. As you can see, it comes with a pair of dual ridge horn antennas which have a very huge bandwidth from 1 GHz up to 20 GHz. So a pair of these horns allows you to take the measurements for any antenna under test, and the gain of these antennas is already calibrated and provided, so one has to replace your antenna under test with the horn antenna. As you can see, one of the antennas is mounted onto a stepper motor controller which can be rotated in steps from 1 degree, 5 degree, 10 degree and so on. The instrument control is through a touch screen TFT 320 into 240 pixels, so we can always set up the rotation of the antenna under test using the user interface provided. As you can see in detail right now that the current position is displayed as 0. The UI logic is standard in that the black and the gray display is the button and the green background with the black numerals is the display. So the current position indicates 0 degree, which is the current angular location. We have a button for a reset position which will reset the current angular location to 0 degree. There are up and down scroll buttons. We can program the end position, which in this case is 360 degrees. We can program the step sizes, which in this case is set to 5 degrees. We can program the forward time it takes to move every step, which in this case is 0.5 seconds. So that will determine how fast or slow the motor moves at each step. The dwell time is the time the motor takes to stop at each angular step, so that the receiver logs the current RSSI level and memorizes in its memory location. The number of steps, the number of cycles right now is 1. That means the motor will go from 0 degree to 360 degrees and it will stop. The whole time is the time it will stop at 360 degree location. So as we press the start button, the motor will start rotating in 5 degree steps, as you can see. Now what will happen is that at each angular step the motor will bring out a pulse of 10 millisecond, which is brought out and applied to the signal analyzer, which in this case is a system which is able to receive frequencies from 40 MHz to 12.4 GHz in 3 bands. The one band goes from 40 MHz to 4 GHz, the other band will go from 4 to 8 GHz, and the other band will go from 8 to 12.4 GHz. So we will switch on the instrument. The instrument has a warm-up time of 1 minute. During the time, the instrument thermal stabilizes its measurements, and at that time there should not be any connected cable to the input of these connectors, because the connectors will be internally terminated and they may pick up some noise which may change the calibration of the instrument. So we are going to wait for about half a minute till the thing warms up. So the signal generator is also being provided, which has a matching frequency range from 40 MHz to 12.4 GHz. The system comes with a pair of these microwave absorbing panels, which are required because most of the time the measurements will be in the indoor environment, and due to the high frequency of the antennas being used, there will be a number of reflections from the walls and the objects around. So these absorbers are pyramidal absorbers which are provided, which will nearly emulate the behavior of an anechoic chamber into an ordinary indoor lab. So this will help us to provide a nearly free space environment for omnidirectional antennas, and the patterns that you get from the system will be nearly as what you would see in a textbook. laptop which is not being provided with the system can be used to download the antenna patterns, and which will be visually be available onto the software which is being provided. Now we will switch on the transmitter. The transmitter is connected via a SMA coaxial cable onto a standard dual ridge horn antenna. This horn antenna has a rotator which can allow the rotation of the antenna in horizontal and vertical polarization. So this is for ease. Right now the antenna is vertically polarized, so the antenna under test has to be vertically polarized. Through one small connector we can rotate the antenna from the vertical plane into a horizontal plane, as you can see. So the antenna under test is always maintained at the same vertical height, and it keeps pointing to the standard transmitting antenna which is being provided. So this arrangement allows for very easy change of antenna under test, and the antenna under test can be measured in azimuth plane as well as elevation planes using the stepper motor provided. Now the controls of the instrument is very self-explanatory. As we can see, the signal generator can be set up to generate any frequency. So in this case, a number of antennas, about 40 odd antennas are provided. A lot of them are operable at 4 GHz, and a number of them are also operable at 10 GHz. So right now we have set the signal generator to provide a 4 GHz signal which is transmitted from the standard horn antenna at the transmitting end. Now we will set up the receiver as well. The receiver can be set up to a frequency of 4 GHz. We will apply the connector, and this connector is connected to the antenna under test. So as you can see, the receiver starts to display the current power level, which is about -55 dBm. The instrument has a huge dynamic range of about 100 dB. As you can see, as we changed the polarization from cross polar to copolar, right now both the horns are in the vertical polarization plane, the power level has risen to about -38 odd dBm. So the system has a very huge dynamic range of about 80 dB linear, and more than that 80 dB we can increase the dynamic range by the use of attenuators being provided. The operation of the touch screen is self-explanatory. As we can see, the operation of the signal generator in this case, the frequency can be incremented by a direct control of the touch screen. It can also be incremented or decremented in the given step sizes. We can also activate RF sweeper mode, which in this case will generate a frequency from 40 MHz to 12.4 GHz. We can set up the step size. We can set up the step time it takes to move from one frequency to the another, and the current frequency is displayed here. Now every time a frequency is moved to the next frequency, a trigger is being generated which is available at the back panel of the instrument. This trigger can be used to synchronize the microwave signal analyzer, which will allow a tracking operation of the generator and the receiver in synchronism to each other. Now we can also do a modulation for the signal generator, which can be amplitude modulation. It has an internally generated 1000 Hz, which will be amplitude modulated onto the carrier wave which is being generated. It is self-explanatory, the controls. We can do a continuous wave, and we can also do an amplitude modulation burst. We can also do a pulse modulation. Again, the on time, off time, number of pulses and the burst duration is programmable. We can also do a FM modulation using an internal generated 1 kHz signal sine wave. We can do it with the external signal which is being applied at the back panel. It has also got a built-in microphone which can be used to set up a communication link between the two antennas. For antenna measurement though, you do not need the modulation, and we will operate the instrument in the CW mode. Now the operation of the signal analyzer is also similar to what the signal generator had. So we had the frequency which could be adjusted and the current power level is being displayed. We can also activate the sweeper mode as is what was in the signal generator. We can also do a power meter. So this power meter right now is designed to monitor the frequency over the IF bandwidth of about 200 kilohertz. So it also displays the current memory location. In this case, the power measured is minus 38.4 dBm. We can change the units from a whole gamut of different units being provided. You can see you've got dBr, dB microvolt, milliwatt, watt, and so on and so forth. Most of the measurements we will do it in dBm mode. We can also do a processing of the received signal strength by doing an averaging or a peak detection or a RMS algorithm. Now, in order to operate the instrument, we will also be using the trigger functions to synchronize the signal analyzer with the stepper motor controller for antenna measurement. So for antenna measurement, we will basically set up the instrument in the auto stepper mode. As you can see, we press the button here, so the instrument starts listening to the trigger pulse from the stepper motor controller. So when the stepper motor controller is put into the auto mode, the instrument will start rotating and it will start logging the locations at different memory locations. We'll continue with the antenna measurement in the next video.